Yeah, camera on everyone. Let's start off. So last thing that we did, the magnetic moment. So let's go ahead. We'll do a few more questions on this. So let's say we have a charged particle Q going in a circle with speed U, radius R. Let's say we have a charged ring. Rotating with omega, charge Q and radius R. Let's say we have a charged disk. Find the magnetic moment of the systems. So in current electricity, we studied, right? If a charged particle is going in a circle, it behaves like a current loop. And if you have a current loop, you have a magnetic moment. How do we do this? I'll show you one. See, first one, it's going in a circle, charge Q, speed U. What is the current? Current is charged by time. What is time? Circumference 2 pi r by speed U. So what is magnetic moment? NIA. Here, there's only one particle, so number of turns is 1. Current is QU by 2 pi r. A is the area of the loop, which is pi r square. QUR by 2. Now here, there is something interesting here. We will see, we'll derive something more generalized. If you look at the magnetic moment here, QUR by 2, if you divide and multiply by mass, this becomes MUR Q by 2M. MUR is nothing but angular momentum. We get Q by 2M into L. So it's quite a useful formula. Mu, magnetic moment. Let's see whether this thing works for the ring and the disk also. Magnetic moment will be Q by 2M into L bar. L bar is angular momentum. valid for uniform charge distributions. How will you do for the ring? Same story. Current will be charged by time, which is 2 pi by omega. Magnetic moment will be I into area. This will be Q omega R by 2. So this can be written as multiply and divide by mass. It will become mr square. This will become Q by 2m. Mr square is nothing but moment of inertia of the ring. I omega. I omega is nothing but angular momentum of the ring. There, that formula is working out. So using the same logic, I can now do the same thing for the disk. I can even extend this to a hollow sphere. Charged solid sphere. We will see one case how to integrate this. So you should know your moment of inertia ka formulas. So mu of the disk will be charge q by 2m, angular momentum of the disk, which will be, what is the moment of inertia of a disk? mr square by 2. Q by 2m, mr square by 2 omega. What is mu of the hollow sphere? Q by 2m. What is the moment of inertia of a hollow sphere? There, if you don't know your moment of inertia values, you will be stuck here. 2 by 3 mr square. What is the moment of inertia of a solid sphere? 2 by 5 mr square. There. So as long as you know it is uniform distribution, I can directly take, moment of inertia and finish it off. Clear with this. What if the distribution is non-uniform? So let's say we have a disk whose charge density sigma is equal to sigma naught x. Meaning this thing charge at the center, it is 0. If you go outside a little more, and more, you're getting, as you go out, the charge is becoming more and more. The radius of the disk is r, and this whole setup is rotating with omega. Find mu of the disk. Let's try to integrate this. So if you have a non-uniform distribution, you don't have an option, you have to integrate. Because this thing will actually behave like a non-uniform disk, so you need to find moment of inertia of a non-uniform disk. Yeah, that means you have to integrate. So if you are going to integrate, then better just do this only. So the advantage is for uniform bodies, right? You already know the moment of inertia, so it makes your life easy. For non-uniform, you have to integrate. Think, I'll give you 2-3 minutes. How do you handle this? So the previous question would be a proper mains level question. They want to ask you something in advance, they will mess up something like this. He'll give you a non-uniform distributions. Let's see. At a distance x, take a thin ring. Dx width. So this is x, and what is the charge on the ring? Charge on the ring will be sigma naught x, surface charge density, into the area of this, which is 2 pi x dx. What is the current on the ring? Current on the ring will be the charge on the ring, which is 2 pi sigma naught x square dx by time. Time is 2 pi by omega. 2 pi will cancel. You end up with sigma naught omega x square dx. Now, what is mu of the ring? Now, be careful. Mu of the ring is current into area of the loop. It is not area of the ring. You're getting it? When I take a ring here, what is the area of the loop? Pi r square, na? So this will be sigma naught omega x square dx. So be careful. Don't write 2 pi x dx. 2 pi x dx will be the area of that, that small thickness card thing. This is the area of the loop. So nothing, we are talking about this area in the middle. A is that area. There, we got mu of the ring. Mu of the disk will be integral mu of the ring 0 to r. This will be sigma naught omega pi r power 5 by 5. Check. Yeah, right, Sash. Yeah. Clear this? Yeah, that's how you integrate. In case if it is a non-uniform distribution, you have to take, depending on the shape, you have to integrate for each part and then add up all the moment of magnetic moments. Any doubts on this? All got the steps. Let's see one more. This is important. This will again see another 2 more times. We have a spiral. It's a tightly wound spiral. Matlab, there are a lot of turns and it is tightly packed. Not able to draw it that way. N is the total number of turns. The inner radius is A, outer radius is B, and the current I is flowing in all of them. Find the mu of the spiral. Yeah, something like that, Pooja. See, how to do spirals. Listen to this thing. You should know the technique here. First thing, number of turns per unit width. So there are total n turns, and the width of this spiral is B minus A. Now, at a distance x, take a ring of thickness dx. Since it is tightly wound spiral, the idea is this. In that dx, there are a lot of turns. It's not a single turn. There are multiple turns in that dx. Number of turns in dx thickness will be n by b minus a into dx. So that many turns are there in this ring of radius x. So mu of the ring will be number of turns, nia. So that will be number of turns will be n by b minus a dx. So the dx is so small, you can assume all the rings have same radius. The current is I and area pi x square. Remember, this is the area of the loop. There, this is the moment of inertia for that ring. Now, if you integrate all these spirals, spiralically, you'll get the integral mu ring. Limits will go from a to b. This will become ni pi by b minus a. That will be x cubed by 3. So that will be b cubed minus a cubed by 3. Check. So that is how you introduce dx curve term in this integration. So the main thing in a spiral, na, this idea is important. No matter when you see a spiral, this is that catch. If you can get that number of turns in the dx thickness, from there the dx integral term will come. It's a tightly wound spiral, so we can say there are a lot of loops in that small space. Clear with this. So this is how you can find mu ka value. So now once you know mu ka value, we know torque is mu cross b. So let's see how to use that torque part. Any doubts on the spiral? We will encounter this in the next one only, magnetic field, and then we'll also encounter this thing in electromagnetic induction. 2 more times you'll see this. Idea is the same. Next one. Let's say we have a current carrying loop. have two strings. Let this tension be T1 and let this tension be T2. So in this loop, you have a current flowing here. So this is going in. Here the current is coming out. So because some people will see in the other direction, you can see however you want. So current is coming out from the left and going in from the right. This is carrying current I. So this ring ka mass is M and radius R. There is also a magnetic field B. Now you switch on the magnetic field. Gravity is anywhere there. So something happens. Because of the current loop and the magnetic field, this ring will try to rotate. But because of gravity is there, it doesn't rotate. But this messes up the tension. So find T1, T2, the tension in the strings. If the ring is at rest in the horizontal position. Let's see how you do this thing. This was a PYQ, but that was more easy question. They asked which one is greater. T1 is greater than T2, T2 greater than T1, T1 equal to T2, something like that they asked. So we will try to find the values. So we have a ring of mass M and radius R in a horizontal thing, and there are two strings along the diameter. So T1, T2 are connected at the diameter. If the current I is flowing and if there's a magnetic field, something happens. The tensions won't be equal. So what is T1, T2? Think. I'll give you a minute or two. Let's see. See. First of all, let's see the direction of this torque. This is the current loop. So if you use a right hand thumb rule, this will be the direction of mu bar, which is NIA. N is 1, current is I, area is pi r square. And here the magnetic field is this way, B. So mu cross B. If you use a right hand thumb rule, you can see the torque is going into the plane. So mu cross B, the torque is this way. Able to see how is the torque? So there, if you look into my screen, if this is the coil, this is the mu bar pointing up. Magnetic field is to the right side. So mu cross B meaning rotation is this way. So the book is trying to rotate this way. Are you getting it? Mu cross B. So that is the direction of the rotation, basically, torque. So this coil is actually trying to rotate like this, meaning if you give enough current, this is what would happen. There is a possibility the loop can become like this. So this side, the string becomes 0. This is how the rotation would be. So if you give a lot of current, this is what will happen. That's why in the question it is mentioned, it remains at rest in horizontal position. Clear with this thing. So the rotation is this way. Are you getting what is happening with the direction? How the ring is trying to rotate? It is trying to lift off clockwise. So anyways, but in our problem, it is given as use your right hand and then you see the directions there. Mu cross B. You can clearly see also now mu bar is in which direction? J bar. This is I cap, J cross I minus K cap. It is into the plane. Got it? So now if you write the FBD of this, look at the forces. We have T2, we have T1, we have mg. That's it. There are only 3 forces. And now we also have one magnetic torque. In the other direction, sorry. We also have a magnetic torque. So system is in equilibrium. So T1 plus T2 is equal to mg. Great. It is also in rotational equilibrium. So if you take torque about center of mass, then we have mg ka torque is 0. T1 is trying to rotate clockwise. Mg is also, magnetic force is also clockwise. So we have T1R plus magnetic torque. The one who is opposing is T2R is equal to 0. So from here we'll get T2 minus T1 will be magnetic torque, which is mu B by R. Two equations, two unknowns. Add them, you'll get T2. Subtract them, you will get T1. There, if mg becomes equal to mu B by R, the tension becomes 0. So they can ask you something like that also. Find the current so that the one of the string becomes loose. Is the picture clear, everyone? All clear with the torque and the directions? Clear, na, Vihan? Arush? Adi? Clear with this? Ahana? Kush? Arnav? Great. Let's see one more. Solid sphere. Mass M, radius R. The ground is rough, there's no slipping. You kept multiple turns here. So you have n turns. Along the equator. Equator, basically the diameter with current I. So you can say mu bar will be like this. Now what you did, you switched on the magnetic field B. Once you switch it off, something happens and this thing won't remain quiet anymore. This thing will start rotating. This is how it will become. This is angle theta. So this coil will start rolling on the floor. Find axis no center of mass, find friction, and find angular velocity as function of theta. So the magnetic torque will start rotating this, and there's a friction on the floor. So this thing will start rolling on the floor. Find the acceleration of center of mass, friction, and angular velocity as function of theta. Theta is the angle with the vertical. Let's see. So let's say after theta, the coil is like this. This is your mu bar. This is your b bar. But you have taken theta with the vertical. This angle will be 90 minus theta. The torque will be into the plane. Are you getting it? So rotation will be like this. So torque magnetic will be mu b sine theta. Theta is the angle between them. Your angle between them is 90 minus theta. Mu b cos theta. Mu bar is nothing but n I area, which is pi r square. So there I know this thing. Now if you draw the FBD of this, what are the forces acting on this? Normal reaction, friction, mg. That's it. There are only three forces. And you also have a magnetic torque. Remember, this magnetic torque is a couple. So for a couple, no matter which point you take, the torque will remain same. Now you tell me, if there is no slipping, what is the best point to take torque? The bottommost point. So this will have acceleration of center of mass and this will have alpha. So we will choose the bottommost point ka torque about A. If you take torque about A, the advantage is F ka torque 0, N ka torque 0, mg ka torque 0, all are gone. The only thing left is magnetic torque. So torque for a couple, no matter about which axis you take, it will remain same. The moment of inertia about will be A about alpha. This will be mu b cos theta. Moment of inertia will be 7 by 5 mr square alpha. So alpha will be 5 mu b 7 mr square cos theta. You want to find omega? I can write this thing as omega d omega by d theta. This will be 5 mu b by 7 mr square cos theta. Integrate this thing, you will end up with omega square by 2 is equal to 5 mu b 7 mr square. That will become sine theta, 0 to theta, that will be sine theta. And this will give you omega. You want acceleration of center of mass? A center of mass will be r alpha. You want friction, there is only one horizontal force, F is equal to ma center of mass. There you get everything. Clear with this? But let's say if I just want to find omega, there is a much faster way. How do you think we can do? The alternate would be this. Initially, the coil is like this. Finally, the coil is like this. So this is mu, this is mu. And this is B, the angle is 90 degrees. This is B, this is theta, 90 minus theta. The initial potential energy is minus mu bar dot B bar, which is 0. Final potential energy minus mu B cos 90 minus theta. Change in potential energy plus change in kinetic energy must be 0. The total energy is same, right? So from here we will get mu B sine theta minus plus u final minus u initial. This will be half mv square plus half I COM omega square. I can use conservation of energy, isn't it? The change in magnetic potential energy is equal to the gain in kinetic energy. Clear with this? Couple as an actual force. What are you talking, Bihan? Couple force क्या relate कर रहे हो?
So means couple does not contribute to ACM basically.
हाँ, ACM comes due to force.
Okay.
There is no magnetic force. There is a magnetic torque. Are you clear with the steps, everyone? If you just want omega, energy is faster. There's no need to integrate, do all this stuff. Because it's not slipping, I can conserve energy. Actually, ये भी हो जाएगा. Once you get omega from here, उसको differentiate करेंगे ना, omega d omega by d theta. That will give you alpha. From there, you can find ACM. You can go in the reverse also. Depends, whatever strikes you. But we have seen something like this before. Remember where? Electrostatics mein. The upper half is positive, lower half is negative. That thing rolls. We have seen something like this. So this thing is also actually an oscillatory motion. This will not keep going forever. After some time, what will happen? The coil ka mu bar will reverse, na? Then the torque will change the direction. So this coil, this thing is going front and back. It is doing an oscillatory motion. Clear with this? There, that is about the magnetic torque. So this is how they'll frame questions on this. So whenever torque is involved, simple rotation will come into the picture. Clear with this? So there. So in magnetic force, we have seen mainly three things. One is F is QE cross B. Next is F is IL cross B, force on a current carrying wire. And third is your magnetic torque and magnetic moment. Next thing, we kept on saying there's a magnetic field B and all, but what is the relation between the magnetic field and the current? So the next part is the magnetic field. Now this is completely experimental, Biot-Savart's law. Just like with Coulomb's law, which gave you the field or the force between two charges, the Biot-Savart's law is also experimental. It gives you a relation between field and the current. So if you have a current carrying loop I, if you take a small DL bar, the magnetic field is given by dV bar is mu naught by 4 pi. You will see some new terms. I dl bar cross r cap by r square. This thing also, right? If you can multiply and divide here, you know r bar is nothing but mod r bar into r cap. This will become mu naught by 4 pi I dl. Instead of writing as r cap, if you write as r bar, it will be r cube. Same thing. Now, if you actually see this formula, it kind of resembles like this. 1 by 4 pi epsilon q by r square. Can you see some resemblance? In place of mu naught, you have 1 by epsilon. Q ka place mein you have I dl cross E, r, and then r square ka place mein r square is there. There. This is the formula you need to remember. Now that formula comes completely from experiment. So there is no derivation or anything for that. So what does each term mean here? So dB bar is your small magnetic field at point P due to the small wire dl bar. dl bar is a small length in the direction of current. So current carrying wire, if you take a small length dl, that will produce a small magnetic field dB, which is equal to this. And the dl bar ka direction is the direction of the current. R bar is a vector. This is important. R bar is not position vector. R bar is vector from dl bar to the point where magnetic field is calculated, to point P. This is something similar to the torque thing. Remember, torque is equal to R cross or R cross F. What is R? Anyone remembers what is that? Let me ask you a question. Let's say force F is 2I minus 3J 4K is acting at origin. If I ask you find torque about 3, 4, 6, how will you find torque? Straightforward question. This is a proper mains level question. A force is acting at the origin. Find the torque about 3, 4, 6. Bas ho gaya question. Can you give? I'll give you a minute. Give me the answer. Solve. Give me the answer. I'll give you a minute. Just to revise you a cross product a bit. Let's see. Mm, 34I plus 17K minus 34I 17K. Yeah, some people did go for as I expected. What is R bar? Here the force is acting at the origin. Your 3, 4, 6 is your axis. So R bar is a vector from the axis to the point where the force is applied, isn't it? So here R bar will be minus 3i minus 4j minus 6k. Yaad aaya? R bar is not the position vector. R bar is a vector from the axis to the point where the force is applied. Clear with this? Be careful. Don't goof it up. Simple question. Unfortunately, both the answers will be there. So when you see R bar, don't think about position vector. Understand the meaning of it. Same thing here also. This R bar is not the position vector. Now we are seeing something new called mu naught. This is something new. 4 pi into 10 power minus 7. This is called magnetic permeability. We will talk about this more in the magnetic materials. We have a paramagnetic, diamagnetic, ferromagnetic. Heard about those? So we will see there. But what it simply means now, just try to look at the formula. I think from there you will get a little idea there. Look at the electric field ka formula. In the electric field ka formula, where is epsilon naught? In the denominator. Means higher the epsilon, more difficult for the field to propagate. That is the meaning of epsilon r. It is like in resistance. Where is mu naught? It's in the numerator. Means higher the mu naught, more easily field can pass through. So mu naught is like conductance. It is opposite of resistance to the magnetic field. So the physical significance is higher the value of mu, the more easily field can pass through. So we define something called mu relative. Unfortunately, physics may lack of symbols. Mu came how many times so far? Coefficient of friction, refractive index, magnetic moment, magnetic permeability. Again, it will come one more time in waves. So yeah, so mu relative is mu medium by mu naught. Just to give an example, iron ka mu relative is 4000. So it is 4000 times more easy for the field to pass through iron than atmosphere or air. So that is a physical significance. So higher the mu, more easily magnetic field lines can pass through. There, for now, just keep that in mind. We will talk about that later again. Clear, everyone? That's it. Technically, this is the only formula we have for magnetic field. So from here, we are going to divide everything else. I think we have around 6 shapes. 6 primary shapes are there. So as long as you know the shapes and the results, the rest of the questions is just only permutations and combinations. We just combine everything. Let's see, today we'll deal with mostly 3 shapes. So let's see a few questions before jumping there. So we have a small wire here. 53 degrees. So we have a small wire of length 2 mm, 2 millimeters at angle 53 degrees with the horizontal, carrying 2 amperes. It's a very small wire. You can almost treat it to be a point. Carrying 2 amperes at 4,4. So this point ka coordinates are 4,4 meters. Length of the wire is 2 mm. The distance is 4,4 meters. So compared to this distance, that is a very, very small wire. Find the magnetic field at the origin. So technically speaking, there is only one formula, So the magnetic field dB bar is mu naught by 4 pi I dl cross r cap by r square. Then if you know all these values, substitute there, you'll get the answer. So it is just a matter of finding all that stuff. Get it? You got a minute. So let's see the values. So mu naught is 4 pi into 10 power minus 7 that I know. Current is 2 amperes given. What is DL bar? It is a 2 mm ka wire at 45 degrees. So DL bar is 2 mm, 2 into 10 power minus 3 meters. You need a vector form. So it is making 53 degrees. Cos 53 I cap plus sine 53 j cap. What is R bar? R bar is a vector from the point to the origin. Remember, this will be your R bar. So R bar will be minus 4i minus 4j. So what is R cap? Minus I minus j by root 2. There. You can substitute all those, you'll get the answer. I'll leave it to you. Clear with that? So it is DL bar. So it is not DL ka magnitude. So just find DL bar. 2 mm at an angle of 53 degrees. Make it I cap, j cap. Sure? Easy? Next thing. Let's say we have a charged particle Q, which is going with velocity V, 3i minus 2j plus 4k. And let's say it is at 2 comma 3 comma 1. So a charged particle is going with some velocity. And we studied in current electricity, a moving charged particle is similar to a current wire. So find the magnetic field at the origin due to this charge. This is a pretty good one, right? Easy, but it's a good one. The formula, I'll give you a general formula. That itself is a question. We know a charge will create electric field, but a charge can also create magnetic field. And these are the key things we ignored in electrostatics. So how will so somehow you have to manipulate the Biot-Savart law to get a charge ka term instead of current. Think. The Biot-Savart law dB bar is mu naught by 4 pi current I dl bar cross r cap by r square. So we can write that current as dq by dt dl bar cross r cap by r square. So this dl by dt ka term becomes your velocity ka term. There. So this is the magnetic field due to a moving charge. Mu naught by 4 pi q dl by dt becomes velocity. So v bar cross r cap by r square. Remember this, quite a useful result. So they'll ask a question like this: find the ratio of magnitude of electric field and magnetic field at the origin. So this will give you the magnetic field, and electric field will be kq by r square. So they'll ask you the ratio of these two things. That is how they'll frame questions. That means if I keep a charge q here at rest, or let's say this charge is also going with v1. Now if I ask you find the force between these two charges, what will you find? If you just find electrostatic force, that will give a wrong answer. Now you have to find the magnetic force also, no? So technically, if two charges are moving, not only there's electric force between them, there's also magnetic force also between them, which we have never considered till now. Are you clear with this? So that was the thing. That's what we call as the Lorentz force. So if you take only electrostatic force and the magnetic force, things will be a little different. Clear with this? Next thing. So let's see some shapes here. The first shape is a finite wire. We have seen this in electrostatics. Anyone remembers the electrostatics ka result? If you have a finite wire, lambda, theta 1, theta 2, d, किसी को याद है? I'll give 15 seconds. Think. Just say it to yourself. When I show, you can verify. This will be k lambda by d sine theta 1 plus sine theta 2. The other one will be in the direction of theta 1, k lambda by d cos theta 1 minus cos theta 2. So that is important, which side it is. It is in the direction of theta 1. Why is that? Because you can take anything as theta 1, anything as theta 2. So depending on what you take as theta 1, it will adjust accordingly. Clear with that? So don't forget that. So here, it's a little easy. So it's not that complex. The result at least is easy. So we have a point P here. Same thing. The angles are theta 1 and theta 2. Theta 1 is the angle with the upper one, and theta 2 is the angle with the lower one, and this distance is d. So let's say at a distance x, take a small segment here, dx. This vector will be r bar. This will be dx bar. So if I take this angle is theta, this angle will be 90 plus theta, and this distance is d. So we want to find the magnetic field due to the dx at dB. So dB bar will be mu naught by 4 pi. Current is I. This will be mod dx mod r cap. The angle between them is sine 90 plus theta by r square. This will be mu naught by 4 pi. That will be dx cos theta. R square will be r square plus x square plus d square. We know tan theta is equal to x by d. If you differentiate it, we'll get dx is equal to d secant square theta. Integration by substitution. So we will get magnetic field dB bar mu naught by 4 pi. That would be d secant square theta, d theta cos theta. Denominator becomes d square 1 plus tan square theta. That 1 plus tan square theta, secant square theta will cancel. We'll get mu naught I by 4 pi d cos theta d theta. We get a pretty decent integration. Therefore, the magnetic field will be, and you integrate this, limits will go from minus theta to plus theta 1. So be careful with that, because theta 2 is downward. We are taking it as minus mu naught I by 4 pi d cos theta d theta. That will be sine theta, but sine of minus theta will be again, it will become plus sine theta. There. The direction I'll show you. So that's it. There's only one component. Unlike the electrostatics one, here the result is not really that complex. And it really doesn't matter who you take as theta 1 and theta 2, because both are addition, they will add up. Clear with this? Now, let me put it in a more usable form. Case 1, if you take theta 1 is equal to theta 2 is equal to 90, it becomes infinite wire. Then the magnetic field B becomes mu naught I by 2 pi t. And what about the direction? We use right hand thumb rule. Now listen, in magnetic field, right, we have only two directions. When you take your right hand, look at the screen. We have the right hand, there are only two directions. We have the thumb, which is a straight line. We have the fingers, which is a circle. Getting it? There are only two directions, a straight line, a circle. If the current goes in a straight line, in this case, the current is going in a straight line, put your thumb along the current. The fingers will give you the magnetic field. So this meaning the field lines are going in circle. Suppose if current is going in a circle, put your fingers along the current, thumb will give the magnetic field. Are you getting it? There are only two directions. A straight line, thumb, circle is the fingers. Current goes in a straight line, thumb will be along that, the fingers will give the magnetic field. Current is going in a circle, thumb will give the magnetic field. So here, put your thumb along the current and try to rotate it. So you will see, you will get magnetic field lines like this. You will get concentric field lines. So on the right hand side, the field is going in. On the left hand side, the field lines are coming out. Are you able to visualize that? The current is going in, you can see the lines are going in and they're coming out from me. The lines are coming out and they're going in. So that's how we use the right hand thumb rule here. So this is the direction of current. This will give you the direction of magnetic field. Clear with that? Yeah, that's the formula for infinity. Case 2, if theta 1 is 90 and theta 2 is 0, you get semi-infinite wire. Luckily, it really not much different. The formula will simply be mu naught I by 4 pi d. Case 3 is the more important one. I taught you something like this in electrostatics also. What if the wire is like this? This is 30 degrees and this is 60 degrees. This is 60 degrees and this is 30 degrees. You're getting the difference between them? How will you take theta 1, theta 2 here? If you remember the derivation, we took theta 2 here negative because theta 2 is down. Once you took a negative, minus of minus, it became plus na here. So if theta 1 and theta 2 were both up, it would have been you would have got sine theta 1 minus sine theta 2. So basically this formula was derived under the assumption theta 1 will be up and theta 2 will be on the other side. Are you clear? So if theta 1 and theta 2 are on the same side, theta 1 will be 60, theta 2 should be minus 30. Are you clear? So be careful with that. So here is the case when you have both plus 60 and 30. Are you clear with this? The formula was derived under the assumption both the angles are on either side. If they're on the either side, in the formula, put them as plus. Clear with this? Clear, na, Devansh? Here we took minus theta 2 record. Don't look so confused. Because the theta 2 is down, you took it as minus theta 2. Because it is minus theta 2, you have a minus of sine minus theta 2 came. That became plus. If both the angles are on the same side, this would have been plus. So you have a minus sine theta 2 aata tha. Got it? So if both the angles are on either side, you'll get plus in the middle. Take a break. Come back by 9:45. We'll continue from here. Any doubts so far? Anyone still confused with this thing? Please ask. You're
सर
still
ये
confused. I know. बोलो.
सर ये उल्टा नहीं होना?
क्या उल्टा?
थीटा 2 माइनस 30 है ना सेकंड केस?
तो वही है ना थीटा 2 माइनस 30. अरे
नहीं नहीं
गॉड,
सर.
तो ऑलरेडी वो यहाँ पे ले लिया रे गॉड. भाई
अच्छा
तो बोल रहा हूँ मैं.
ठीक.
बिकॉज इट वेंट डाउन, तो यहाँ पे लिमिट्स में ऑलरेडी माइनस थीटा 2 लेके तुझे ये फॉर्मूला आया था
ठीक है.
ना. अगर ये ऊपर होता था दिस वुड हैव बीन प्लस, देन यहाँ पे माइनस आता था. गॉट इट. भाई बोल रहा था दिस फॉर्मूला वाज डिराइव्ड अंडर द assumption थीटा 2 नीचे है. So this was the formula was actually for this guy. Sure? पक्का ना? सेम थिंग क्या था इलेक्ट्रोस्टैटिक्स में, एक बार रेफर कर लेना. चलो कम बैक इन
सर
5 मिनट्स.
सर सर डाउट
हाँ, क्या देते हैं?
सर पेज 72 पे
क्या हुआ?
सर इसमें वो हमने आई को लाइक करंट को आई ही लिया बट वॉन्ट द करंट एड अप लाइक बहुत सारे लूप्स है ना तो जितने
इसलिए
लूप्स.
नंबर ऑफ टर्न्स लिया ना रे गॉड.
अच्छा
नंबर ऑफ टर्न्स आया कहाँ से थे?
हाँ ठीक है समझा.
इसलिए ना n into y इज द टोटल करंट, इसलिए नंबर ऑफ टर्न्स आ रहा था.
ठीक है थैंक यू.
आदित्य गॉट समथिंग? चल कम बैक व्हेन 9:45. There, so that's about the finite wire. Next thing, a current carrying arc. This is more easy. So if you have a current carrying arc carrying current I, so if you take a small piece here, RD theta, which is nothing but your DL bar. This is perpendicular and this will be your R bar. This angle is theta. So by Sawat's law, dB bar is mu naught by 4 pi. The current is I, DL is RD theta, and the angle between them is already 90 by R square. So if you integrate this, integral mu naught 4 pi R d theta. So this is a good way to write. So field due to an arc at center, write like this thing, theta by 2 pi into mu naught I by 2r. So if you put theta is equal to 2 pi, p is equal to center for a full ring, your formula becomes mu naught I by 2r. There. So you can remember for the full ring. Remember, this is for one turn. If there are n turns, you'll multiply into turn, into n. That's for an arc, and this is for a ring. The direction is given by, again, the right hand thumb rule. If the current is going in a circle, put your fingers along the current and thumb will give you the magnetic field direction. Clear with this? You can note down the result. Note down this result also. I hope you noted down for this finite wire and infinite wire. You should remember the results. There you can note down this thing also. You can remember for the arc or the center. Like if you remember for the center, you can always use unitary method to get the arc. So now if you see this thing, this current carrying loop, this is kind of equal to a magnet actually. They do behave similar. So if you look at the field lines, this is how the field lines will look. And if you look at a magnet, you will notice there's a similar profile for the field lines. So you can say a current carrying coil is similar to a magnet. Technically, you can't tell the difference between the field lines. So this idea is important. So later on, when we do certain problems, you can compare this coil to a magnet and you can solve problems. That is about an arc. The next thing, the field on an axial line. If you have a current carrying coil of radius r, let's say you want to find the magnetic field at a point P here, at a distance x. Here the field lines are going in and the field lines are coming out from here. So what we do here, we take a small piece here, dl bar. Again, derivation is not that important. So this is your r bar. This will be already perpendicular. It's like a cone here. Are you able to visualize that? It's like a cone. So all these points will be like part of a cone there. This is your r bar. Now formalize what db bar is dl cross r bar. So it's perpendicular to both r bar and dl bar. So the field will be like this. Be careful. In electrostatics, the field will be along r bar. In magnetic field, the field is perpendicular to r bar because it's a cross product vector, na? It should be perpendicular to the dl bar. So if you take this angle is theta, this angle will be 90 minus theta. That means only the horizontal components will add up, all the vertical components will cancel out. So the magnetic field at point P will be integral dB cos 90 minus theta. So if you use your Biot-Savart's law, mu naught I by 4 pi, that would be sine theta. That would be mod dl by distance is r square, which is r square plus x square. So here everything is constant. Actually, theta is also constant for a given x. Theta is constant. The only thing you have is dl there. Mu naught I by 4 pi. Sine theta is opposite side, r by this thing. So you will end up with r by r square plus x square whole power 3 by 2. This is integral mod dl bar. Dl bar is the length on the wire. So that will come the circumference. There. So field on the axial line is given by mu naught I r square by, this is different from your electrostatics formula. R square plus x square whole power 3 by 2. Anyone remember the field in the electrostatics? K q x by r square plus x square 3 by 2. Do you remember where you get the maximum field? R by root 2. Yeah, ये सब याद रहना चाहिए, basics है ये. This is the kind of questions you'll get in CET and mains. So let me just put on the result. If these kind of questions will come in CET, you have 50 questions and you have barely like 45 minutes to solve. Even at a main thread, out of 25 questions, you'll find at least 7 to 8 questions of this sort, which will feel very simple, but people still go up and come because they don't remember. So B actual will be n. N is the number of turns. So remember, every time whatever we are deriving is only for one turn. So you have to multiply that n if there are n turns. R square plus x square whole power 3 by 2. So if you try to plot the field for this, so unlike the electrostatics field, here the field is maximum at the center. So it will be 0 on that side and 0 on this side. You'll get maximum at the center. And the field lines will look like this. So this formula will give you a result only in the axial line. You cannot find at any other point. There, these are our 3 shapes. Like I said, there are 6. We are doing 3 shapes today. First one is a finite wire, arc, and the field on the axial line. So this is also part of a circle only. You can put on that result. You should definitely remember this result. Matlab, directly that result itself is a question. There was a question like this in mains once. Find the point on the axial line whose field is 1/4 of the field at the center. Matlab, he is asking at a distance x. At the center of the field is b. Here the field is b by 4. Find x. बस हो गया. मतलब if you know the formula, you'll get the answer. You don't know the formula, you're gone. Great. Let's see a question. So we have three infinite wires along X, Y, Z axis. Let's say this X axis is carrying current I1. The Y axis is carrying current I2. The Z axis is carrying current I3. We have a point in the XY plane, which is X comma, Y comma, 0. Find the magnetic field at point P. Three infinite current carrying wires along XYZ axis. I want the vector form I cap, J cap, K cap. Let's get this. This is a good one. If you understood this, I think you got the directions part. These are infinite wires. What is infinite wires ka formula? In case you didn't copy, mu naught I by 2 pi d. What is d? D is the perpendicular distance. Try. I'll give you 2 minutes. Take your time, get it. We have done something same problem in electrostatics. There it was 3 wires of lambda 1, lambda 2, lambda 2. Find the electric field. Let's see. So first of all, let's look at this red one. So see, current is going in x-axis. So put your thumb on x-axis and rotate your fingers. Can you see how it is? So the field is going up here and then it is coming down here. So if you see the field lines, here it is going up. Here it is going down. Are you guys able to visualize? So on that xy side, it is going up. So at point P, the field will be up Bx mu naught. Current is I1 by 2 pi d. D is the perpendicular distance. So for x-axis, what is the perpendicular distance? For x-axis, the perpendicular distance is y coordinate, isn't it? 2 pi y k cap. Are you clear with that? For x-axis, the perpendicular distance is y coordinate. For y-axis, perpendicular distance is x coordinate. What about this y-axis? Put your hand in the y direction and try to rotate it. You will see on this side, the field is down. On this side, the field is up. Are you able to see the direction? So this field will be downward, which is by, which is mu naught I2 by 2 pi x minus k cap. So for this guy, the perpendicular distance will be this. Sure with this? What about the z-axis? Let me do this separately. So for the z-axis, this is your point P. So this will be the perpendicular distance. The field will be like this, isn't it? It will be in the xy plane. Put your thumb here and rotate here. So you will see this will be the rotation. There, this will be the direction BZ. So what is BZ? BZ will be, remember, if I take this angle is theta and this is x comma y, that distance will be root over x square plus y square. So this will be mu naught I3 by 2 pi. Perpendicular distance is x square plus y square. What about the directions? Let me see it in the top view. If you see this from the top view, this is how the circle looks. This is BZ, this is theta, this is theta, this is 90 minus theta. There. So that will be BZ minus cos 90 minus theta, so minus sine theta I cap plus sine 90 minus theta cos theta j cap. That's your vector form. What is tan theta? Tan theta is nothing but this height is y and this is x. So tan theta is y by x. Got the BZ, everyone? So the BZ will be in the xy plane, making this is the magnitude and this will be the vector form minus sine theta I cap and cos theta j cap. All clear with this? And the perpendicular distance will be root over x square plus y square. These two are fine. So add this up and you'll get the answer. Any doubts on this? Pretty good question. It's just based on infinite wire. You just have to keep adding it up. Any confusion on bx, by, bz? Anything that you're not clear, ask. Vihan. Clear? Next thing. So in the first case, the current I is going in the equilateral triangle. It is just going in the loop. In this case, the current is going and coming out from here. In this case, current enters and current leaves from here. O is the centroid. Equilateral triangles, side A. Find the magnetic field at the centroid. Magnitude and direction. Root is missing in BZ. 2 pi D ना सही बोल रहे हो. Let's get this. Get the first one. B and C, what are the catch? We'll see. Again, we are just using finite wire ka formula. An equilateral triangle is 3 finite wires. Give them a try. See the first one. Someone got an answer. 9 mu by 4 pi k. I think so. That looks right, Niharika. Let's see what. So for the first one, so just take any one of them. You can just do into 3 because if you look at the directions, all will be in the same direction. So for this guy, if this is the centroid, if you drop the perpendicular, remember this is the perpendicular distance d. This is 60, this is 60. And the field direction, use right hand thumb rule, it is into the plane. So B due to one wire will be mu naught I by 4 pi d. The centroid divides in the ratio of 2:1. So this will be A by 2 root 3. And the angles are sine 60 plus sine 60. So B at the centroid, and you can see all the 3 wires will be in the same direction. It will be 3 times B of the wire. Clear? What about the B part? Check this answer. If you got this, you're done. I will leave the calculation to you. What about this B and C? Why are they looking so weird? Let's talk about B. See. First of all, let's see the triangle ka part. Now, there's no need to calculate anything. You will see something. So when the current I is entering here, we know current will split in the ratio of 1:3. So this will be I by 3 and I by 3. Now this I by 3 will give a field in the downward direction. How much? I don't know, but let it be B. This also will give B. Here the current will be 2I by 3. This will give 2B in the opposite direction. Can you see this? That means B at the centroid will be 0. Check the directions. There is nothing to calculate actually. You can just see and say it is 0. So what is the thing about those side wires? The catch is this. If you clearly notice here, these wires here, which I'm pointing, I'm clearly showing you it is passing through O bar. So if you take a vector here, DL bar, and if you take a vector here, this is R bar. So DL is parallel to R bar. Therefore, these wires will not create any magnetic field. So it is important I show the wires actually. So most people write in the exam, they'll give you the third case and most people will answer the second case. Now see the third case. Now you will understand the difference. In the third case, these wires are not passing through the centroid, right? So even those wires will create magnetic field. Those are semi-infinite wires. That is a catch in B and C. Are you getting it? So that is the reason, if you see, I was clearly showing you it is passing through centroid. In the B case, it is still not over. There is something more you can do interestingly. See, B case, you will notice, forget about a triangle, you can even take an n-sided polygon. For example, if you take an hexagon, if you send current I from here, and if you take out current I from here, you will notice same thing here. Current will split in the ratio of 1:5. This will be 5 by 6. So this one guy will generate a magnetic field 5 times B. Here it is I by 6, I by 6, I by 6. So you will have 5 fields pointing downward. B at the center is 0. So it doesn't matter how you take. If you take an n-sided polygon, so if the current enters and current leaves, now don't get confused between case 1. In case 1, current is flowing within the loop. So if you take an n-sided polygon, it doesn't matter from where the current enters, just make sure it should pass through the center here, and doesn't matter where the current leaves from. The B at the center is 0. You can extend this even more to a circle, because a circle is a n-sided polygon where n tends to infinity. So if the current enters here and current leaves from here, the currents will distribute in such a way B at the center is 0. Pretty good result to remember. Again, works only for regular polygons. Clear with this? I showed you for a triangle, but I can show this for anything. It works. The current will always redistribute in such a way they'll cancel out at the center. Now, can you do the C part? So the triangle thing is still 0. The headache is the wires outside. So exam they'll get C question. You will write the answer for B and come. Split this into 3 parts. So one wire like this. So centroid is here. This is that case 3, yeah? Can you see both the angles are on the same side? This will be your perpendicular distance D, which is A by 2 root 3. This angle is 60 and this angle is 90. So here theta 1 is 90 and theta 2 is minus 60 because both are on the same side. That's why this question is pretty good. People will realize it is there and they'll mess up. Or if you don't like this, you could have done this also. You can take semi-infinite wire and you can subtract one side now. That also works. You can take a semi-infinite wire till this point and then you can take this finite wire like till here and subtract it half wire. Then you can work it out however you want. So what is the field for this guy? Mu naught I by 4 pi d, which is A by 2 root 3 sine 90 minus sine minus 60. About this triangle, we saw this thing, this will be 0 due to the triangle. Because in a triangle, the currents will split like this. Again, this will be same as this guy. This also will be B only. So the answer will be 2 times B. Clear? Clear with the steps, everyone. That's what makes this question good. The wires outside are creating the magnetic field, not the triangle itself. So the orientation of the wires will matter. Any doubts on this? Clear? I'll leave the calculations so you can check. That will be 1 minus root 3 by 2. I'm not sure you'll get a good answer. Okay, next thing. Let's say we have one turn, radius r. Someone took this, it was cut, and then it is rewound to n turns. We have done something like this in magnetic moment also. Same current. Find the ratio magnetic field before and after. Hope you remember the field due to a full ring. U naught I by 2r per one turn. Right, Vihan. Right, Aditya. Right, Arush. So, what is the magnetic field initial? There's only one turn, so mu naught I by 2r. Remember, the length of the wire remains constant, so 2 pi r initial circumference into n into 2 pi r. The total length must be same, so r is nothing but r by n. So in the second case, the magnetic field, now there are n turns, and each turn will get a magnetic field of mu naught I by 2 small r. So this will become n square b1 there. So magnetic field becomes n square times. Clear? That's an easy one. Let's say we have two arcs like this. Find the magnetic field at the center. You're right, Purvada. Right, Aditya. Get the second one. I'm more interested in the second one. That's an infinite grid, huh? Matlab it's just going till infinity. Let's see. Right, Ahana. Most people figured out the second one. You'll get a Lonka series in the second one. So in the first one, if you see, let this guy go this way. I'll keep it in red. So this guy ka field is actually downward. And the other one, the green thing I'm marking, that field is upward. So both are in the opposite direction. So field at the center will be theta by 2 pi. It's for arcs. Mu naught I by 2. Now the radius will be 1 by R2 minus 1 by R1 k cap. So the R2 is outside and R1 is inside. So science will take care of it. That whole thing actually is a negative term. Same thing here. If you do theta by 2 pi mu naught, current is same. Take out R also common. You'll end up with 1 minus half plus 1 by 3 minus 1 by 4, so on till infinity. This is minus k cap. There is nothing but ln 1 plus x. X is equal to 1 ln 2 series. Mu naught I theta by 4 pi r ln 2 minus k cap. Got this? Clear? Remember, we saw in ln 2 series in electrostatics also for potential. Any doubts on this? You can see equations are like this. When once you know the formulas, it is just, you're creating different kind of things and you keep finding the fields for them. So main thing in the second part of the chapter is you need to know the results for each shape. That's a 3/4 of a circle. Find the field at the center. So here current is flowing like this. It goes in a semicircle. Then it comes out. Are you getting the second shape how it is? You can look at my screen. It is like this thing. See, current is coming here. Look at my headphones. It's like this semicircle. So current is coming, going through a semicircle and goes off from here. That's like this. Able to visualize that? So that semicircle is out of the plane. First one, there is a thing. Be careful. I'll give you a hint. See, look at the first one. If I have drawn like this, and if I drawn like that, is there any difference? Both are not same. Did you get the difference? The difference is this wire, isn't it? That guy also will create field now. If I had given like this, then outside wires will be 0. So that's what I'm saying. You have to be careful with the wires which are coming from outside. You just can't see the circle. So now get it. Right, Aditya, ऐसा कुछ आएगा. Yeah. Hi by 8. नहीं रे. They won't add up रे. दोनों में एक पाई का डिफरेंस आएगा. Try. I'll give you a minute more. Get the directions, everything properly. Let's see. हो सकता है B part. Check your answers. So here, let's divide this into 3 parts. So there's this part, and let's draw it again. So you have this part where the center is O. This is R. This is a semi-infinite wire. So this guy ka field will be, look at the direction. It is into the plane. It is out of the plane. Yeah. Mu naught I by 4 pi d k cap. Then we have a 3/4 of a circle. This is also out of the plane. B2 will be 3/4 of a circle, which is mu naught I by 2r. Are you getting it? When you add them, there's 1 by pi there, so you can't directly add them. So be careful with that. And the other guy, it is passing through this, so B3 is 0. Add them, you'll get the magnetic field. Got this? And for the other one, so for this red wire and this red wire, these are infinite, semi-infinite wires. So if you see, the field will be down and down, so we'll get B and B, where B1 will be mu naught I by 4 pi r. This green one is a semicircle. It will be this way, B2, which is half of the circle. So mu naught I by 2r. This would be I cap, and this would be your minus j cap. There. So the field will be mu naught I by 4r I cap. That will be 2 times. So 2 times mu naught I by 4 pi r j cap. Got this thing? Both the fields are perpendicular. All clear with this? There. So that is how they can mix and match, these arcs and wires and everything. That is one part of it. So next class, when we catch up, we'll continue from here. After this, we have few more shapes. We have 3 more shapes. One is a infinite plate, and then we have solenoid, toroid, and we have something called Ampere's law. So mostly next week, we will wrap up the chapter. And after that, we'll start off with EMI also. And bar magnets, we will see later on. That's a completely mains ka thing, a lot of formulas. But that's it. This whole chapter is like this. As long as you know the formula, questions will be pretty straightforward. We'll try to see some more higher level questions. But I think by next Friday, we will wrap up the chapter. Okay, with that, we'll wrap up for the day. So hope everyone has given the test. So I'll see you guys again Monday at same time. So take care, stay safe. So any doubts, anything, please stay back and ask, or else you can leave.